Wang. Over to you.
Okay. Thank you very much. It's also my first time to be here for this conference, and it's a great honor to be here, and thanks for the invitation. So I'm going to give you a brief summary about the recent activities we have around these large language and audio models. You probably have already come across a lot of work on large language models, but here is a cutting edge between large language models and large audio models. And also we will demonstrate the applications to some of the downstream tasks in audio processing. This is, of course, a joint work with many of my PhD students and colleagues. And here is the outline. I start with the introduction about where the problem comes from, and then we discuss the motivation for developing large audio models and large language models, and the combination of large language and audio models. And we will show some examples and the methods how fuse and combining audio and language. And also we discuss the open challenges in this area. And we will also discuss the integration of the audio language models and then demonstrate such models in applications to some of the downstream audio application tasks. For example, audio captioning, audio question answering and reasoning, and text-to-audio generation, and controllable audio editing, and neural audio codecs. We will conclude and summarize potential future work. So just a bit about my background. My background is on audio processing and machine learning applied to audio and speech processing. So some of the tasks we have considered, for example, audio source separation and localization tracking, and more recently we have done a lot of work on audio classification, tagging, and search and retrieval, and also rendering. So the model we have been playing with, including physics-based models and also perceptually motivated models. But here today, I'm mostly focusing on data-driven models, especially based on machine learning. And we learn models from trained models by using data. So the data we worked on, including both audio-only data as well as multimodal data involving audio, image, text. So conventionally, we play with a lot of on physics-based models or statistical models for audio processing. But in recent few years, we have a lot of activities in terms of developing so-called general or universal audio representations by using large-scale audio data set. So this is essentially we actually learn neural network models, which is able to perform many different tasks, including audio classification, separation, and retrieval. Here I highlight some of the popular models. For example, PANS is the model we developed in 2019 and 2020 using the data set from Google released in 2017 audio set. Yeah? And we developed this PANS model, which is built on convolutional neural networks. This model now have been used by many people. And you can see the trend that more recently, there's increasing interest on developing large audio models using unlabeled data. We call it self-supervised learning techniques. We can actually learn strong audio representations without having to rely on labels, right? So we can use unlabeled data to train such self-supervised models. Here we have a few examples, including ASIT. This is a model we developed on self-supervised techniques. Yeah. So now I show you just briefly the PANS model we have developed based on convolutional neural network. This is the model we trained on audio set from Google. This is the data set contains 1.6 millions of audio clips. And in terms of the features, we use the combined one-dimensional feature from convolutional neural networks, and as well as two-dimensional features, which is time frequency spectrum. So I show you a demo to show how good it is in terms of this model applied to this audio set for classifying 527 sound classes. Here we only show the top 5 sound classes. On the top left of the demo, we show the probabilities estimated by using this model. This is the demo. The sound clips are taken from YouTube, randomly taken from YouTube. You can see how good it is for classifying such audio.
Okay, no more. No more. Okay.
Horse.
A high school girl's been murdered. Mr. Harrison's daughter is missing.
Okay, you can see this is one of the model we have built. And of course, in recent few years, you all know that large language models also experience significant advancements. For example, especially since 2017, the emergence of transformer model. So this is essentially have actually pushed the field quite significantly. And then since 2017, there are large number of models developed for processing language text, right? For example, you can see the ChatGPT and GPT-4 at the moment. There's GPT-4o, which is not only able to process text data, but also sound and image as well. So there's a lot of development in this area. So why actually we're interested in this? If you look at one of the paper published that large language model, the reason why people are interested probably because there's strong capabilities if you increase the model size. For example, initially it's 8 billion parameters. You can do some tasks like a question answering and language understanding. Now, if you have 540 billion parameters, so there you have many more capabilities which is emerging because of the scale up of the models. You can see that, for example, summarization, you can even do arithmetics. So there are a lot of capabilities with large language models. But my interest is more on the cutting edge between audio processing and language models. So why we want to do large language and audio models. And so these provide opportunities to solve some of the conventional audio signal processing and understanding problems. For example, we could use this to address the limitations of audio models in zero-shot or few-shot classification. And we could also use this for multiple tasks in audio processing. And we could also extend these capabilities of audio models to new tasks. For example, from extending from audio classification to audio captioning and question answering or reasoning, and audio generation to storytelling and controllable editing. We could also use this for audio source separation in an innovative way. For example, I can demonstrate here now. Conventionally, when we do audio source separation, we take the sound mixtures and then we separate into individual sound sources. Now we can do is we guide the model or we instruct the system using language. For example, this is a sound mixture contains sounds of vehicles and also people chatting. Now, if I instruct the system, say, okay, the engine sound of a vehicle, then the model is able to separate out the individual sound sources that you instruct the model to do. Could you play the sound clip, please? The mixture.
Random. So I've just made 2 methods. I haven't really created them, but this is how I'm going to deal with them. And before I...
Okay, and then the separated one. So you can see that the engine sound has been well separated from the mixed sound, which also contains the voice from speaker. Yeah, so that's what you can do now, but is not able to do before. So what's going on right now in the field? You can see that there's a lot of development in this field. On the top left, this black text actually, this is popular models in speech processing, like including speech recognition, where they combine large language models to solve some of the speech problems in speech recognition, speech source separation, and many more tasks. And then on the bottom left, this is to do with music. You can see there are a lot of models for combining music processing with language models. And then on the top right is for general sound, like sound effect, environmental sound, not limited to speech and music, but any sound. Yeah. So we also have developed several popular models. This is on the bottom right. You can see that this is a models. I will show you a little bit more later on. And here are the data set, popular data sets you could refer to if you want to work in this domain. That, for example, we have this audio caps as a relatively small data set. But in recent years, there's increasing activities. This is a larger data set we developed. For example, wave caps and sound wave caps. We will actually show some slides later on. And this is about on the top right, this is the data set for audio question answering. Yeah? And trends and open questions in this field. And here are, based on my understanding, the open challenges that we still face in this domain. For example, how to fuse the audio information with text information. So, we have spent a lot of effort in this domain, and also application to the downstream audio tasks. And extending to multimodalities, not just audio, but image and video. And data scarcity, there's still a lacking of high quality data set in this domain. So there's a lot of effort have been spent on creating data set. Without data set, we are not able to build such models for these problems. And of course, there are also many other problems, for example, low resource language support or real-time processing. At the moment, the models are relatively large. And if you have limitations where we require it's resource constraint, limited memories or processing capabilities, in this case, you have to adapt the model to these scenarios. So there's a range of different problems. And how to fuse audio and with language. So this is a few different ways to do that. For example, you could align audio and text using contrastive learning techniques. You actually map the embeddings into the joint embedding space of audio and text. You could also tokenize audio. Audio is continuous signal. Text is discrete. So what you can do is you discrete, we call it tokenized audio. You turn continuous signal into discrete tokens of audio, right? Then you can use a large language model to process audio in the same way as you process text. And you could also use other techniques like using transformer, the cross attention, like Q-former techniques to fuse them. There's also other ways to do that. And now I quickly show you some of the tasks we have worked on to demonstrate where this large language and audio models could be applied. The first task is on audio to text generation. It's also called automated audio captioning in the literature. Essentially, what you do is you take an audio signal and then you try to build a system that is able to describe the content of audio using human language. Here we talk about English, right? For example, you take the audio clip, and then you want to describe what's in the audio clip. Here, for example, a woman talks nearby as water pours. You could also use some other language like German, French, whatever language you have, but here we talk about English, right? And where this could be used, there's plenty of applications you can think about. For example, audio retrieval. Before we type a keyword on YouTube, Google, and then you try to identify the audio clips, right? But now you could describe in a paragraph or a multiple sentence to precisely describe what you want. And then the system is able to identify that. You could also use this for subtitling TV programs, especially general sound. Now you have the subtitles for speech, but not for background general sound. So now you can use such system to do that. And how to do that? Because of the limitation of time, I'll probably just quickly explain the idea. So what you could do is you take the audio clips, right? You use some kind of models to compute audio representation, data representation. This is essentially features of audio. You could use, for example, convolutional neural networks to do that. And then you actually merge this audio information with text information. In training, we have text information. For example, you compute word embedding from text, and then you use, for example, cross-attention. This is a typical transformer architecture. You actually fuse the audio information, these are the audio features, with the text features. And that finally you get this so-called audio-text joint representation, and then followed by linear layers and a soft mask that will give you the probabilities of the word from the vocabulary that are selected to represent this audio signal. So that's how the text information are predicted based on such models. This is the one of the first model we have built. This is also now widely used. And of course, there's a lot of challenges there. For example, humans describe the text in different ways. There's a diversity of captions. There's also a multilingual captioning. At the moment, most work on focusing on English, but this could be extended to other languages as well. And just to show you a demo to show that how good it is with such system, the input to the system is the audio signal, and the output is the text you will see on the top. So that's the text actually predicted by our model.
Then what you might want to do is add just a little bit of oil.
You're pushing it, Professor.
All right.
Okay. Jerry Coyne is the...
Вот так мы кормим птиц.
So Adam, what's for breakfast this morning?
So now we can do with large language models, you could input to the system an audio signal, audio clip, and then you also ask a question about this audio signal. You could say, how many sound events in this audio clip? So that's question. With this question, the model should be able to understand first the question, right? This is posed as a text. At the same time, you have to analyze the audio signals. What's in the audio? And you could ask many open-ended questions. So this is the front end in this domain. And, recently, we have developed a model called audio prompt, acoustic prompt tuning system, which is able to analyze multiple audio signals and comparing or summarizing what's happening in the audio. And you can pose any open-ended questions to the audio. For example, we have, in this case, we have two audio signals. We use the audio encoder to compute the features, and then we align them with the text information, and that finally use some kind of complicated models to project this audio into discrete tokens. So then we can use large language models to process the audio tokens together with text tokens. So essentially we treat audio just like text. Right? After you turn continuous audio signals into discrete tokens, we can process in the same way as language. So finally, we can answer the questions you posed to the system. For example, how many sound events in total? So if we, we present the system with 2 audio clips, and you ask such questions, the system is able to analyze the audio signals and analyze your question and then provide such answers. Yeah, that's called audio question answering and reasoning. Here I show you the example. The first example is cracking sound. The second one is the measures sliding sound. Can you play these 2 sounds, please? So the question the question we asked to the system is, in which recording are the sound events more evenly distributed? So that's the question we posed to the system. So the answer is second. Indeed, you probably get, after you hear the sound, you get the sense, right? The second one is more evenly distributed in terms of the sound event. So that's the kind of high-level semantic questions we ask. And the model should be able to understand that and to answer that question. So I want to skip that. The third task is on text-to-audio generation. Text-to-audio generation the task is opposite to audio captioning, where in this case, we want to generate sound just based on a human's description. This could be used in many applications, for example, in game, in film production, and you add background sound to animations. In this case, you don't have to go out and capture the sound using sound devices. You can use a model to generate sound just based on your instruction. For example, dog barking, bird chirping. And here we have developed a model like audio LLAM. Now this is also a very popular model used by many people. So basically, you try to actually map the audio with text into a joint latent space. And then you learn, for example, a latent diffusion model that is able to predict the latent of the audio features or latent vectors Z. Finally, you can use some decoders to decode into time frequency spectrogram, and then use a vocoder to turn that into waveforms. So this is the model that can be used to generate sound based on text information. And we have also extend this model to a more advanced version called Audio-queried 2, so where we actually leverage these capabilities of large language model. In this case, we use GPT-2 as the text encoder. And for audio encoder, we use this audio MAE. And then again, we use a latent diffusion model to generate sound based on the conditions like audio and the text features. I won't go into details, but if you're interested, that we have a paper on here. And I just show you a demo. Now, this is a long demo. I will have to jump, only play part of that. So basically, this is a text input to the system. Yeah? For example, a traditional Irish fiddle playing a lively rear. And then the model will be able to generate the sound.
The Secret Service did not, at the time of the assassination, have any established procedure governing its relationships with them. The prisoners were in due course transferred to Newgate to be put upon their trial at the Central Criminal Court.
Well, if you want to really grow kind people, there's a lot you can do when things are good and when you are full of joy. What we grown-ups might call restitution. If you break something, you fix it, whether it's a broken toy or hurt feeling. If anything, Scarlett talks even more about the other side of an apology, forgiveness.
When one child hurt another, many of the mothers responded with something casual and bland.
So in that interaction, you're giving children a lot of language to describe how they're feeling.
And then storytelling, this is aligned with the audio idiom work. This could be used as a tool for creating stories for audio. Basically, you just write a script, and the model will be able to generate sound based on your script. Yeah. So I won't play this demo because this there's not much time. And the fourth task is for controllable audio editing. Basically, you input to the model the sound clip, and then you instruct the model what you want to do. For example, adding horse sound, or drop some sound, or replace the sound, replace dog barking by bird singing, for example. So you can do a lot of things by modifying the audio just based on your language instructions. We have a model called Wavecraft that can be used to perform such tasks. And finally, this neural audio codec. Conventionally, we have audio codec like an MP3, right? This is based on psychoacoustic model. But now you could use this neural network model to do that, to encode the audio sound. This is the recent development. You build this audio compression or decompression models just using neural networks. And we have developed a model called the semantic codec, which is able to compress the audio to very low bit rate, but maintain very good fidelities. And we use this so-called semantic codework as well as acoustic codework, and we reconstruct the audio using latent diffusion model. So this is the current state of the art in audio compression and decompressing. And I can show you just one demo quickly of speech, please.
However, as the two forces came nearer together, Button Bright spied Trot and Captain Bill standing before the enemy, and the sight astonished him considerably.
And the code.
However, as the two forces came nearer together, Button Bright spied Trot and Captain Bill standing before the enemy, and the sight astonished him considerably.
So that's this audio. Yeah, it's only 350 bits per second. So it's probably the lowest bit rate we can achieve in the current state of the art. So you can play with this model. It can be used for speech, music, and environmental sound effects. So quickly, we have built this data set like sound VE-caps and the audio set data set you can use for building the large audio language model. So as a summary that we have discussed large language audio models. Sorry, it's a quick run, but in terms of future work, there's a lot of potentials to develop like unified models for understanding and generation, and also leverage or improve the controllability in terms of these downstream tasks. And finally, we have a demo for dance generation where you can generate dance videos from music. The music inputted model, and the model is able to generate a 3D dance video. This is ongoing work, so if you're interested, yeah. And finally, all our work have been open sourced. You can download the data set, code, as well as demos from these links. And this is the stuff you can take home if you are interested in any of this work. And thank you so much.
Thank you. Thank you, Professor Wenwu Wang. Thank you.
Sorry.
I love the little dance. I love the little dancing avatars there. They're really cute. Can we get those? Great. Do you have questions for the professor? Yes, over here. Yes. Here we go.
Thank you. Have you considered compressing the audios using machine learning or artificial intelligence? Or have you come up with some models which can really compress good, like having a better compression technique?
You mean other techniques, non-machine learning techniques?
No, machine learning techniques using, so for the compression, you just saw some slide, yeah. But what is the performance or how good they are? So.
Yeah, and in compression, the common challenge is to maintain the fidelity of the compressed audio. At the same time, you try to reduce the bit rate. You try to compress the audio signals to as small as possible, right, in terms of bit rate. So this is a common limitations, but the current models often are limited in terms of the bit rate. They can only compress the audio to down to 1 kilobits per second. It could go up down to 700 bits per second, but the quality is not guaranteed. So there's actually a trade-off. And the semantic codec we have developed is not only able to maintain the fidelity, but also achieve very low bit rate. And the reason is because we actually used the two codeworks, semantic codeworks, and as well as acoustic codeworks. And at the same time, we use a latent diffusion model. This is much more powerful as compared with many other existing models which are built on GAN network, which is a generative adversarial network, is not as good as the diffusion models we have applied. Yeah.
Right, we have another question here at the back of the room.
Hello. My name is Masinisa, and thank you very much for the presentation. And my question is regarding your format of the inputs. And more precisely is that how robust is the input handling and feature extraction from the input itself? Are you sensitive at all to sampling rates, frequency differences, and also the different types of the same sound, but different shapes of the, let's say, frequency domain? And second part is regarding the transformer architecture that you presented, and you showed that you are directing the search with the queries and values from the sound itself. So basically you needed to have to encode those and go through tokenizing them. How individualistic your tokens regarding sound, if I compare this to...
Repeat the final question.
How individualistic your tokens, if you compare this to images, let's say, bad quality image to good quality image, but the same pixel value and same pixel position in a 2D grid. But since here you are in a time domain, frequency domain with sound, so the positioning does not even matter here. So what kind of changes did you have to go through your architecture, transformer architecture, in order to adapt this, to be able to go from sound to speech or text, sorry.
Okay, yeah, all right. So the first question is about, different input, different frequency of audio, or how robust, for example, how sensitive our models are. So in terms of building the model, we have to rely on some data sets. So at the moment, different data sets are actually using different sampling frequencies. And some like 48 kilohertz, some are like 16 kilohertz sampling rate. And in terms of the reliability or how good the model built on one particular sampling rate, whether it is able to generalize to other sampling rate, we have performed some tests. So sometimes we do have issues like losing the performance a little bit, but not as much. For example, if we train the model on 16 kilohertz, if we want to apply the model on like 48 kilohertz, then so usually either you directly generate sound for 16 kilohertz and then upsampling that, but the performance will not be as good as if you directly train the model on 48 kilohertz. So that's kind of mismatch, or we call it gap in terms of the domain. That's an issue, but in terms of performance, the degrades for performance is not so significant. You can still use that, yeah. And in terms of the second question is the transformer model. The models we have built is usually we train the model on, for example, 10-second audio data, 10-second, yeah, audio clips. If you have much longer ones, then you would have to chop the audio into smaller blocks. Every block is like 10 seconds, and then you concatenate them. It's possible to generate much longer audio clips using the model, but you have to because the model is only trained on text with audio, but each audio clip is 10 seconds. So that's mainly is limited by the data set we have used to build the model. And there are also audio data sets where you have the audio clips which is longer than 10 seconds. For example, the data set like 30 seconds. And in that case, we also have a way to work with such data sets. But in terms of training the model, and if it's too long, then you have to think about the match between text and the audio. Yeah, this is also a practical issue we have to deal with when we train the model.
Right.
Yeah.
Thank you.
Thank you.
Thanks for your questions. That's all we've got time for. We can keep that discussion going during the break. You're going to stick around for a little while?
Yeah.
Great.
Thank you.
Fantastic. So I mean, it's complicated how difficult for large language audio models to process sound. Are humans still better at it, at processing sound?
I think large language can deal with some of the very complicated questions.
Yeah.
Especially, if for human to understand sound, you have to listen to the whole signal, right? If it's 1 minute or 2 minutes, you have to finish the whole, listening to the whole sound before you can make a judgment.
Okay.
But human tends to be getting tedious when they listen to sound for like consecutively 1 hour or 30 minutes.
An example here.
Yeah,
yes.
So, but now there's an opportunity for AI models. You can listen to the sound no matter how long it is.
Okay. So they are better than us.
Yeah. So definitely AI model can do something. For example, even for the reasoning task, we showed that it can understand sound to a certain extent, like a reasoning. For example, if the clock tick 5 times, human will understand it's 5 o'clock, right? But conventional model is not able to do that. But the large language model may be able to do that because in many textbooks, it's written like, tick 5 times, it's 5 o'clock.
Okay.
And this is written in text, even though the model never heard about the sound, but is understand the semantic meanings.
So some things it's better than us, some things it's going to be better than us. Okay, pretty soon. Okay, that's clear. Hey everybody, thank you very much to Wenwu Wang. Sorry, Wenwu Wang, apologies. Wenwu Wang.